Hello everyone, and welcome again to another, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and we'd also greatly appreciate if you consider supporting us as well. So please check the link in the description or click the join button below for more details. My name is Sava, and today we're investigating a key concept that has numerous applications in credit risk modeling, for example, but goes beyond that. That is binomial correlations, which are correlations between yes or no events. We have investigated the binomial distribution, its derivation, applications, and approximations in a couple of prior videos, so please check these out if you're just interested in the fundamentals of the binomial distribution. However, today we are interested in inferring whether the events that we observe in some binomial-ish sample are independent or correlated. And as usual, we will start with a very simple and intuitive example or illustration of the method, but we'll discuss how to quite easily generalize it into economic and financial applications as well. So let's consider the following. We have got 21 years where a cohort of 70 students sits some exam, and we can record how many of the students in every single year passed this exam. And obviously we might want to know whether the successes or failures of individual students are correlated or not. For example, to detect whether there is collaboration between students when they're taking the exam, and we might not want that. Or we might want to check whether there are systematic differences year on year. So whether the exam is approximately the same in terms of difficulty, or the difficulty varies. So successes or failures of students become correlated naturally through that. For this diagnostic, what we can do is we can use the binomial correlation formula to extract the implied correlation between two individual attempts that we've got in our data, two individual students sitting the same exam. Obviously, from the sample that we've got, this parameter is unobservable, but we can infer that from this particular formula. We can exploit the year-on-year variability in the pass rate and relate it to the average pass rate in the denominator here to extract the binomial correlation coefficient. And what is even cooler is that we can test for significance of this correlation coefficient using a t-distribution, as this coefficient is approximately t-distributed with n-2 degrees of freedom, as usual, where n is the number of students in the cohort. So first of all, we have to calculate year-on-year pass rates by dividing the number of students who passed the exam in a particular year, for example in 2000, by the total number of students in the cohort. So we can divide it by F1 and lock the row here, getting pass rates around 70% in each of our years. We can see that sometimes the pass rate is pretty high, like almost 76% here, almost 79% here, and sometimes it's pretty low, for example 63% only in year 2015. And we'll exploit this year-on-year variation in the pass rate to infer the binomial correlation over here. For that, we need the average pass rate, just the average across our 21 years, and the standard deviation of the pass rate, so sample standard deviation formula, and the same data is inputted. And now finally we can apply this very formula. In the numerator we would have standard deviation of pass rate squared, the variance, and in the denominator we would have average pass rate minus the average pass rate squared. That would give us an estimator of correlation between two individual attempts of 0.0123. So quite low but positive correlation. But bear in mind that this particular approach always gives you positive correlation estimations, as it exploits the variation. So it doesn't really examine in which direction the attempts are correlated. So this might as well have been a negative correlation, all things considered. This is just the caveat of this particular approach. However, when you are doing binomial correlations, you are most commonly assuming that they are either independent or positively correlated. So this particular quirk does not harm the estimation process that much, but keep that in mind always. And to understand how likely it is that such a correlation arises due to random chance alone, we can calculate the standard error of our estimator using the square root and then a ratio of 1 minus correlation squared in the numerator and n minus 2 in the denominator. And we get a standard error of 0.12, which gives a t-stat of around 0.10, which is a very low t-stat, but we can confirm that the result is statistically insignificant by plugging it into a two-tailed t-distribution, inputting the absolute value of the t-stat, and n minus 2 again as the degrees of freedom, giving us a p-value of 92%, which is way above conventional confidence intervals of 10%, 5% to 1%, which renders our estimator insignificant, meaning that it's very likely that two students taking the exam have independent probability of success or failure, which is good news for the exam given the fact that there's unlikely any collaboration between students, and it's unlikely that the exam varies tremendously in difficulty throughout the years. But why is this method so frequently used in credit risk modeling? Well, consider this. Instead of the number of students, here we could have number of companies. And instead the number of students who passed the exam here, we could have the number of companies that defaulted on their debt. And this is now becoming a crucial method for estimating what is the correlation between defaults for bonds or loans of individual corporations. And that is one of the foundational building blocks of the CreditMetrics model, simply because you cannot estimate a correlation between defaults using sample data alone. You might as well proxy it using a binomial correlation and exploiting the historical variation in the default rate for a particular class of bond. So for example, here you would have AAA bonds or BBB bonds or whatever, and here you would record how many of them defaulted in every single year. And then you would proceed with exactly the same calculations, extracting the correlation between defaults of two individual bonds. Obviously, another inherent assumption in this particular approach is that all of those two-way binomial correlations are the same. So the sample you're investigating needs to be similar. For example, students sitting the same exam, or if you are dealing with default correlation, bonds or loans from companies with similar credit ratings and from similar sectors to avoid heterogeneity biases. So this approach is not necessarily that foolproof as you might imagine, but it's very useful to get a first glimpse of whether your binomial data is independent or not. And that's all there is for binomial correlations and significance testing using the approach presented. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, finance, or economics you would like me to record. And please don't forget to subscribe to our channel and consider supporting us on Patreon. Thank you very much, and stay tuned.